So welcome back. Welcome back. Um, as we were just talking about, the distributions of sample proportion conditions. So this is, again, the sample means. In order for us to use the normal curve from these sample means, we must meet these conditions, and there's three of them. The first one is the randomization condition. The sample should be a simple random sampled of the population. So you'll be given this information. You'll have to then make a statement whether or not it is or is not randomized. And it must be in order for us to use the normal curve or the normal model. The second condition is the 10% condition. If sampling has not been made with replacement, meaning that you return before you draw again, then the sample size n must be no larger than 10% of the population. So again, this is where you prove or disprove that you will be able to use that normal model. And the third is your success failure condition, where you have to look at n and p and n and q. And again, this deals with categorical data, and you'll look at that later on. The sample size has to be big enough so that both the number of trials times the probability of success is greater than or is at least greater than or equal to 10, and the number of trials times the probability of failure is at least 10. So we need to expect at least 10 successes and at least 10 failures to have enough data for sound conclusions. So again, we're checking NP is greater than or equal to 10 and NQ is greater than or equal to 10. So all we need is for the observations to be independent and collected with randomization. And we really now don't even care about the shape of the population distribution. Well, it does have to be finite, but we really don't care about its shape. And this is called the central limit theorem. Now, by definition, according to the book, is the mean of a random sample has a sampling distribution whose shape can be approximated by a normal model, and the larger the sample, the better the approximation will be. So again, think back to when we rolled 5 dice and we averaged those, then what that distribution really looked like compared to the, let's say when we looked at the 2 dice, and the 5 looked definitely a lot more normal than the one with 2. So we need the mean and standard deviations. And again, this now, we're switching gears a little. Instead of looking at categorical data, we're now looking at quantitative. So now when we're looking at quantitative data, the syntax a little changes a little. So the standard deviation of y bar, the mean, falls as the sample size grows. But it doesn't fall very quickly because, again, you're not dividing by n, but the square root of n. And the book both uses SD, standard deviation of y bar, is equal to sigma over the square root of n, or actually sigma of y bar. And this means the standard deviation of the mean y bar is equal to sigma divided by the square root of n. So please be careful with this because you have sigma of y bar and sigma. And some people think that these two things are both the same. So please be careful with that. Sampling distribution model for a mean as well. When a random sample is drawn from any population with a mean mu and a standard deviation of sigma, its sample mean y bar has a sampling distribution with the same mean, but whose standard deviation is sigma divided by the square root of n. And again, this is quantitative data. So let's take a look at the difference. When we have categorical data, we calculate a sample proportion p hat. Its sampling distribution has a normal model with a mean at its true population. And again, we talked about this in class with the Greek letter p, which is pi, but we really don't use pi for this, because it would just be confusing, because when you see pi, you're thinking 3.14159 and not necessarily like the average or your mean of some population. So we don't really use pi, we use another form of p. So please be careful with that. So again, when we're using categorical data, we calculate the sample proportion p hat. Its sampling distribution has a normal model with a mean at its true population p and a standard deviation that's equal to the square root of pq divided by n. And we talked about that earlier, the pq divided by n. So this is categorical data. And likewise, quantitative data is what we just talked about just a moment ago. When we have quantitative data, we calculate a sample mean, y bar. Its sampling distribution has a normal model with a mean of the true mean, which is at mu, and a standard deviation that's equal to sigma divided by the square root of n. So notice again, when you have categorical data, you have a sampling proportion, which is p hat, and your standard deviation is pq divided by n, and this is all square rooted. And you have quantitative data where you're dealing with a sample mean that deals with your mean is y bar, and your standard deviation is sigma divided by the square root of n. So let's talk a little bit more about this central limit theorem and the three conditions that must be met in order for us to use them. And again, then you'll be able to use the normal model, etc. So the first one is your randomization condition. The data values must be sampled randomly, or the concept of a sampling distribution really doesn't make sense. And again, it has to be randomly sampled. The second thing is that it has to be independent, and there's like an assumption here. Then the book really talks about there's really not a way to check this in general. However, when the sample is drawn without replacement, we should always check the 10% condition. So when we're talking about independence here, we do have to look at this and make sure that we're thinking about it mutually independent, that from one sample to the next, they're not dependent on one another. We really don't want that. You can't use it if they're dependent on one another. So you really have to look at the data and to see if the conditions show that they are mutually independent from one sample to the next. And then the 10% condition, again, the sample size n is no more than 10% of the population. And lastly, the large enough sample condition, and we'll discuss this more in chapter 14 when we get to it, but for now, you'll have to just think about your sample size in the context of what you know about the population, and then tell whether you believe the large enough sample condition has been met. And we'll in the next chapter we'll also come up with the numbers for this and how you're able to do that. So again, I'm going to pause here for switching videos.